Welcome to the Explainer. Today, we're cracking one of the biggest cases in the history of mathematics, a mystery that had the greatest minds stumped for centuries. So you've got these two enormous problems. On one side, you have the tangent problem. That's all about figuring out the exact speed of something at a single precise moment, the world of derivatives. Then, over here, you have the area problem, calculating the super-specific area under some wacky complicated curve. That's the world of integrals. Now, for the longest time, everyone thought these were two totally separate, incredibly hard challenges.
But what if? What if there was a hidden connection, a secret passage linking these two mathematical worlds? This is the question at the heart of our mystery. And believe me, the answer changed absolutely everything.
To solve this, we've got to look at our first piece of evidence. It's this really clever, really powerful idea called the area function.
Okay, so instead of thinking about area as just one static number, I want you to picture it dynamically. Imagine it's a value that's constantly growing, accumulating, as you slide from left to right along that x-axis.
Let's make this real. Take a simple line, like f of x equals x plus 1. Our area function, we'll call it a big f of x, is just telling us the size of this shaded region at any point. See? As we move x to the right, that shaded area just gets bigger and bigger. It's a function that's spitting out an area.
And this is the breakthrough question. We know the area is changing. We can see it. But can we measure exactly how fast it's changing at any given instant? This one question is the key that's going to connect our two mysteries.
This is it. This is where we find that secret connection, the big aha moment where this whole case starts to break wide open.
So imagine we just nudge our point x forward by a tiny, tiny amount. We'll call that little nudge h. When we do that, we add this super thin sliver of new area under the curve. The entire secret to this whole thing is hiding inside that tiny sliver.
Now here's the cool part. If that width, h, is ridiculously small, our little sliver of area is basically a perfect rectangle. And we all know the area of a rectangle, right? It's just height times width. Well, in our case, the height is just the value of our original function, f of x, and the width is our tiny nudge, h.
Okay, so we want to know the rate of change of the area. Does that phrase ring a bell? It should, because that's exactly what a derivative is for. Remember, the whole definition of a derivative is just a formula for finding the instantaneous rate of change of any function. For us, we're looking for the rate of change of our area function, that big f of x.
So let's just substitute that into the derivative formula. The top part of that fraction, right, the change in area, we just figured out that's basically f of x times h. And when you plug that in, this is where the magic happens. The h on top and the h on the bottom just cancel each other out.
And we're left with this absolutely shocking reveal. The derivative of the area function is just the original function itself. Let that sink in. The rate at which the area is growing is literally just the height of the curve at that exact point. The tangent problem and the area problem, they aren't just related. They are perfect inverse operations of each other.
So now that we've uncovered this incredible secret, we can do way more than just admire it. We can actually use it to create an unbelievably powerful shortcut.
You have to understand, before this discovery, finding the area under a curve was a total nightmare. It meant trying to add up the areas of an infinite number of impossibly thin rectangles. It was brutally tedious, and a lot of the time it was just impossible.
But the fundamental theorem of calculus, the FTC, it's like a master key. It turns that infinite problem into two dead simple steps. First, you just find a function whose derivative is the one you started with. We call that an antiderivative. Then, you just plug in your endpoint and your start point and subtract. That's it. All that infinite complexity solved with a little subtraction. It's insane.
And this right here is the theorem in all its powerful, compact glory. That scary-looking integral symbol on the left, the one that represents that mind-bending problem of infinite sums, well, it turns out it's equal to something so simple. Just the change in its antiderivative from point A to point B.
All right, this all sounds amazing in theory, but does this incredible shortcut actually work out here in the real world? Let's take a look. Okay, picture a car that's moving, but its speed is changing over time. We have the function that tells us its rate of change, its velocity, and what we want to find is the total change in its position, its displacement, over 8 seconds.
This is a perfect job for the FTC. I mean, velocity is just the derivative of position, right? So to go backwards from the rate of change to the total change, the theorem tells us all we have to do is find the integral, and we now know that's the same as finding the area under that velocity curve.
So let's use our two-step shortcut. First, we find the antiderivative of our velocity function. Then, we just plug in our end time, 8 seconds, and our start time, 0 seconds, and subtract the two results. The calculation itself is pretty straightforward.
And boom! There's our answer. The car's final displacement is exactly 4 meters. No infinite sums, no crazy calculations, just 2 quick steps of algebra. It's just an astonishingly elegant solution.
And this answer actually highlights a really important difference between displacement and total distance. The integral gives us the net change. What happened here is the car moved forward for a bit, and then it actually reversed. So, while it covered a total of 8.5 meters of ground, its final position was only 4 meters from where it started. The integral nails that net result perfectly.
So, case closed. After all that, what's the big takeaway from solving this centuries-old mathematical mystery? What did we really find?
Look, the fundamental theorem of calculus is not just some other formula. It's the grand, unifying theory of calculus. It's the bridge that connects derivatives and integrals, proving once and for all they are two sides of the same coin. It turns an infinitely hard problem into simple arithmetic, and in doing so, it unlocks countless real-world applications in physics, engineering, economics, you name it.
And that's really what makes this theorem so profound. It shows us this beautiful, hidden unity in the world of mathematics. And it kind of makes you wonder, right? What other ideas out there that seem totally separate, maybe in your own job or your own life, what if they have a secret connection just waiting to be found? That's the power of a great explanation. It doesn't just give you an answer, it leaves you with a much better question.